Hello everyone. Today I'm going to talk about what is reinforcement learning and Markov decision process. This is needed for some of the papers I'm going to discuss in the coming days. So let's get started. So let's see what is reinforcement learning and planning. But before that, let's see what is the famous reinforcement learning loop. Okay, so in the famous reinforcement learning paradigm, you have an environment with you and you have an agent with you, right? So the goal of the agent is to interact with the environment, and the environment will return certain things to the agent. And this particular loop continues till infinity or till a fixed amount of time. So at every time step, the agent will take a particular action, the environment will execute the action, and it will return the next state and the reward corresponding to taking that action that was decided by the agent. For example, at each state, let's say you start with the initial state S0 and you take action A1, you will reach a state S1. And then on state S1, you will decide what action is to be taken next. You will take action A2 and you move to S2. Similarly, this process continues till you reach the end state, which is represented by S tau in this case. This sequence of state, action, next state pairs, that means state, action, next state pairs, is often known as an episode. In this case, the episode is of length tau plus 1. Sometimes it is also called tau, right? The goal of the agent is to learn a policy denoted by pi at given st that maximizes the expected long-term reward. So let's first see what that means. So the goal of the agent is to find a policy pi at given st. So given a particular state st, you have to decide which action should I take, and which is denoted by this function pi, which is nothing but a probability distribution over all the actions that are possible in that particular state st. And your goal is that at each time step you are not only getting the next state, you are also getting the reward corresponding to that particular state, right? Your goal is that you want to maximize this expected long-term reward. That means that you want to maximize expected sum over t rt, right? Okay, so this expectation is decided on various distributions. For example, it may be the case that when you start at a particular state and you take a particular action, you may or may not end up always in the same state. For example, in the case of a windy environment, let's say you have a robot with you, or let's just draw an example here. Let's say you have a grid world with you and the robot is standing here, okay, and you are given particular actions, that means up, down, left and right. Okay, so a agent can take, or the robot can take, any of these four actions, up, down, left, right, and at a given point of time it is standing in a particular cell. Okay, so this is giving you the S0, that means the first state. The goal of the robot is to learn a policy such that it reaches a goal cell that is being denoted by G here, right? So by taking any of these four actions at a particular time step, okay. So when we have this with us, we will start with this. Let's say the robot took an action up, okay, at that means A1 is equal to up. So robot will move to this particular state. Then let's say it decided to take the action A2 is equal to right. But this particular action will have no effect on the position of the state. That means it will return to the same state and the robot will remain on the same state. Then let's say A3, it decides to come on the left hand side. So it will move to this particular state. So it took this particular action, then it stayed in the same state, then it moved to this particular state, and so on and so forth. The episode will continue. Now this is a deterministic setting. Determinism means that whenever you take a particular action, the next state is always fixed. But let's say there is another environment in which case there is a wind blowing from right to left. That means that with some probability, right, let's say if you take an up action, then with probability 0.9 you will actually reach the upper cell, but with let's say 0.1 probability you will reach the upper left cell. So in this case, the environment itself is stochastic. That means it is probabilistic. It will always sample from this particular distribution and decide where the next state is going to be. So that means that in the initial state S naught, which was given by this particular grid, there are two ways R can land after taking A1. That means it can be here or it can be here. That means there are two possible states with probability 0.9 and probability 0.1. That okay. So now you have to maximize the long term reward. Let's say when you move to the exactly upper cell, you get a probability or you get a reward of 100, but when you move to the upper left, you get a reward of, let's say, 1000 for whatever reasons, right? So now the reward function itself is varying based on where you are actually landing in the next state. That means the environment is stochastic, so you have to maximize the expected long term reward, which is given by this particular expectation. So this expectation is over two probability distributions. One is pi, that means the action that you are going to take, how it is going to affect the, because that is how it is going to affect the next state also, as well as the probability of next state given current state and the action you took in the current state. Okay. For example, why is it dependent on the policy pi, which is again a distribution over the actions that you are going to take in given a particular state? Is that because let's say you take a policy, any policy can be a policy, right? Any sequence of actions can be a policy. It may or may not be an optimal policy. It may or may not lead you to a goal. But for example, this can also be a policy that you always take the left action independent of which state you are at. So in this state, if you are in this state, you will move here. In this state, you will move here. And similarly, you will always move here. But after reaching here, you will always stay here. You will never go anywhere because you will keep on taking the left action, which will lead you to the same particular state, right? So this is a policy by definition, but it is not a good policy, right? So now what type of policy you have also decides what type of next state you are going to get, and hence it has control over the reward that you are going to get in the next state. So we want to maximize this. In the case of mathematical formulation, an RL problem, or in fact even a planning problem, is represented using something called Markov decision process, which is a tuple of 7 elements. Let's go through these 7 elements one by one. So S is the set of all possible states. For example, in this case, a robot being on a particular state, particular cell is a particular state. So in this case, there can be a total of 9 unique states, because a robot can be in any of these 9 cells that we have, right? The actions is a set of actions that the robot can take. This is set of all actions. That means there are 4 action in our case. We will come to transition function and reward function now, and a transition function gives you 2 probabilities. First, rather one probability, that what is the probability of next state given that you are at a particular state ST and you took a particular action AT, right? So for example, this is a transition function, that if you are in a particular cell with and you take an up action, okay, so that means you will reach 2 states. One is the upper state, upper cell, and one is the upper left cell, right? So we will have a probability distribution over 2 cells. For example, this is upper left, this will be 0.9 and this will be 0.1. So this is the transition probability. Okay. Similarly, if your reward is stochastic, it will also give you what is the RT plus 1 given ST and AT. Sometimes we also include ST plus 1, right? Because in this case, ST plus 1 is also important. For example, in the case again, if you are at a particular cell, you take the up action, then you can get 2 rewards. One reward is of 1000 and one reward is of 100. So you have again a reward function with these values, right? So reward function is an input function of 3 things. That means it will be function of current state, the action you took, and the next state you landed in. right? And it will model the probability that what is the distribution over the possible rewards. Okay, horizon is the number of steps you are going to take in a particular episode, right? So for example, in the case where we had a policy where we always went left, it will infinitely get stuck in a particular cell, right? So in this case, we will have to end the episode sometime. So in this is called a finite Markov decision process. For usually you can keep it as anything. For example, in certain games it can be 1,000, 100, anything. It is a function of the environment you are defining. S naught is the initial state. In this case, this particular grid orientation is the initial state where R is at the lower right cell, and gamma is the discount factor. Now this is an interesting thing. Gamma is a real value that belongs to 0 and 1, and it dictates how much you are going to value the reward you got from the current state that you are at or a future state. For example, what can happen is that in case of reinforcement learning or planning, when you are deciding a particular policy, the problem with that could be that you may end up focusing too much or on the future state, right? So what they do is that the long term reward, which is usually denoted by GT, which we saw is that nothing but sum over T RT, correct? So long term reward, expected long term reward. In this case, the problem with this is that let's say you have R naught plus expected value of R naught plus R1 plus R2 and so on R tau, right? The problem with this is that if it is a case where let's consider two cases where R tau is equal to 10, rest everything is 0. Otherwise, let's say R1 is equal to 10 and rest everything is 0. In the both the cases, so what is this case saying? This case is saying that at the end of an episode, independent of what you do, you will get a particular reward of 10. And this says that at the start of the episode, you will get a reward of 10. So in this case, what will happen is that while the expected long-term reward will come out to be same in both the cases, the behavior of the policy should ideally be different in both the cases. The policy here in this case should focus on the long-term reward, and in this case on the short-term reward. So how do we control what do we want our agent to do? So what we can do is that we add a gamma term here which decays over time. Which decays over time. So this is the gamma term, right? And this is the reward term. So because t is greater than 1 and it is increasing, and gamma belongs to 0 and 1, let's say you keep it as a 0.9. So as you increase t, that means as t increases, gamma decreases, right? So that means that you focus more on the near short term rewards rather than the long term rewards. So that would imply that you have a gamma term here that will say gamma raised to power 0, gamma raised to power 1, gamma raised to power 2, gamma raised to power tau, right? So as t increases from 0 to tau, the value of gamma raised to power t decreases. So you are focusing more on the short term rewards as compared to the long term rewards, right? Okay, so this is the story of what gamma is. So once we have defined these particular 5 or 7 pair tuple, we are good to go. We are good to go to apply any sort of reinforcement learning or planning algorithm, right? The difference between planning and reinforcement learning is that in the case of planning, you are already provided the values of transition and reward functions. But in the case of reinforcement learning, these are unknown to us, right? So if these probability distributions, that what is going to happen if I take a up action or what is going to happen if I take a left action is provided to you, then it is called planning problem traditionally, otherwise it is called a reinforcement learning. Okay, so let's relate it to something that we have seen in our life. So question is that is our life a planning problem or a reinforcement learning problem? So because no one has told us what is going to happen when we do a particular step, right? So it is not given to us. That means it is a reinforcement learning problem. So, but one can argue in this case that, but I already know that if I take an forward step, I will move to the next position, right? If I take a backward step, I'll move backward, and if and so on and so forth, right? If I stand in the middle of the road, I'll probably get hit by a bus, right? But while these transition functions you already know, they are not provided to you. That is something that you have learned, right? As a child, as a very very small child, the child is not provided with any of these transition functions, and it simply learns by trial and error, and that is what reinforcement learning is all about. For example, a child initially will never know whether a particular pot is hot or cold, right? It will have to first try it and get hurt, cry about it, and then it will get a negative signal, and eventually it will learn. So it will associate the action of touching something with a negative reward. Eventually, over a period of time, the child will learn the distributions over it in a very hand wavy form initially, and then later on in a very concrete form. So hence life, one can say that it is a reinforcement learning problem rather than a planning problem. Okay, so that's all for today's video. We'll continue with the next set of topics, that is multi-arm bandit, in the next video. Thanks.